Perfect, sir.
Okay, great. So then we'll start. We start with the session, right? So it is going to be a 1 hour session, a simple demo of theory of machines. So let me first tell you about theory of machines. Uh, so what are the different? Let us first see what are the different topics. What are different chapters, right? That you will have to study in theory of machines. So chapter 1 will be simple mechanisms. Chapter 2 will be velocity and acceleration analysis. Velocity and acceleration analysis. Chapter 3 is the same order in which we are going to learn in class: gears and gear trains. Chapter 4 will be kinematic and dynamic analysis of single slider crank mechanism. Chapter 5 will be, so I hope you're following. Can I get a yes from you? Can you hear my voice?
Sir.
Yes, sir.
Yes, great. So, okay, fantastic. So the chapter 5 will be flywheel. Then we'll go to governors. Separate checks will be governors. Or we might actually do governors at last. Chapter 7 will be balancing. In balancing, we'll learn two types of balancing. One will be rotary and one will be reciprocating. Balancing of rotary masses, balancing of reciprocating masses. Chapter 8 will be gyroscope. And chapter 9 will be your cams and followers. Cams and followers. Right? So these are the 9 chapters. So in total, out of these 9 chapters, how many marks can you expect? How many marks can you expect in theory of machines? In theory of machines, out of these 9 chapters, you can expect somewhere around 7 to 8 marks. Somewhere around 7 to 8 marks you can easily expect out of this, right? So this is going to be a very conceptual and crisp chapter. If you have learned the topics properly, there are no chance that you are going to miss any question from this chapter. So maximum number of questions you will get from simple mechanisms, maximum number of questions you will get from simple mechanisms and gear trains, right? Thereafter, yes, from flywheel, repeated questions every 2-3 years, every year once questions from flywheel be asked, right? And recently, every 2-3 years question from balancing, every 2-3 years questions from gyroscope, every 2-3 years questions from cams and followers are being asked, right? So you can see this is a crisp chapter. So what will be the total duration of this course? The total duration of this course will be somewhere around 25 to 30 hours. Depending on the response from the class. If the class is responding good, if they're able to understand it easily, the classes might actually, we might be able to finish off the syllabus in somewhere around 25 hours. And if the class is going a little bit slow, the students are taking some time to understand, then it might extend up to somewhere around 30 hours. So how exactly we are going to approach this subject? Okay, the approach of the subject will be completely with respect to GATE point of view. So we have analyzed the last 35 years GATE question papers. The last 35 years GATE question papers, whatever has been asked, everything will be covered, not a single topic will be left behind. So the method of teaching and method of learning will be same. We will solve few questions that has been asked in GATE, that are from good standard books or that have been asked in engineering service, ISRO, from good exams, good questions. We'll solve it in class. Then I will provide you with assignments. Assignments, you'll have to solve it at home, right? The assignments will be in synchronization with the classes. So after each class, I will tell you which of the questions that you can actually attempt. So what you have to do, you have to attempt those questions at home, right? So whenever you're coming to next class, right? Or might be after after 2-3 classes or after 4-5 classes, we'll have a doubt class, and in that doubt class, we'll solve all the questions from your assignments. We'll not keep the doubts to the end. For example, after every 2-3 classes, we'll have a doubt class where we are going to solve the questions from the assignments. This is how we will proceed, right? So let us have a small demo of the first chapter. Let us have a small demo of the first chapter so that you'll be able to understand what exactly the chapter feels like. What exactly the chapter feels like, right? So let us have a small demo. Let us have the initial basic portion of simple mechanisms, right? Okay. So are you guys ready? Can you hear my voice?
Yes,
Yes, sir.
sir. You can go ahead.
Yeah. So so the class has to be responsive, right? Even when this is through WebEx, you might find a little bit difficulty. Otherwise, we have options of chat, we have options of polling. You have already gone through all those things, right? You've already seen those things. So we need to make our class interactive. Only then you will be able to grasp the maximum amount of concepts, right? Okay. Let us see. So what exactly is a mechanism? Leave the term simple. Why simple? We will discuss it later on. First, let us try to understand what exactly is a mechanism, right? So if you talk about mechanism, it is something like you imagine your body. You imagine your body, every body has a different shape, right? Or every living being has a different shape, right? The human body, the humans, they look something different. The elephant will look something different. The tiger will look something different, right? The giraffe will look something different, right? So basically, every machine has a different look. For example, your car is a machine, it has a different look. Aeroplane is a machine, it has a different look. Your IC engine inside the car, that is also a machine, it has a different look, right? So there are, you see, all the machines will look different. But if you go inside, if you take out the outer cover, if you try to rub all the, for example, in a human body, if you try to take out all the muscles, all the tissues, what you are going to get is this skeleton, right? The skeleton is what gives the shape and structure to the body. Take any living organism, if you remove, if it is a word, let us consider mammals. So if you remove the flesh, the tissues, what are you going to get? A skeleton, right? It is a skeleton that actually helps in moving, helps in doing all the mobility of that mammal, right? Similarly, in machines, if you try to remove all the unwanted things, what you're going to get inside is a kind of a skeleton. If you want me to show you the skeleton of an IC engine, this is the skeleton of an IC engine. And all of you know this. All of you know this. This is the skeleton of an IC engine. But does the IC engine exactly looks like this? If you take it out from car, you'll not be able to recognize it. This is also, you'll get to learn. This is also the skeleton of a compressor, a reciprocating compressor. This is also the skeleton of a reciprocating compressor. So this mechanism you can build up to an IC engine. This mechanism can be built up to an compressor also, right? Both are two different machines. Okay. So in this chapter, if you want to build up a machine, if you want to build up any machine, first you have to understand how the skeleton works, how each and every linkage works. What is the relationship between the velocities of different links? What is the relationship between acceleration of the different links. If the piston moves by distance x, how much the crank will rotate? How many degrees will the crank rotate? So all these things has to be determined first. Only after that you are going to build up the machine. You will give a structure to it so that you can actually conveniently use that. So this chapter is all about mechanisms. We'll see different types of mechanisms, how different mechanisms are formed, what is the smallest part of a mechanism known as, right? So how are different mechanism classified? Okay. So all those things with respect to mechanism. In this chapter, we are going to study all mechanisms. That is the skeleton of a machine, the basis, the genesis of a machine, from where the machine is going to be formed. After this chapter, what you are going to study, you are going to study velocity and acceleration analysis. The second chapter will be velocity and acceleration analysis. So what we are going to do, after learning mechanisms, we will try to find out if the piston is moving with a velocity of say 5 meters per second, what will be the velocity of the crank? Or if the crank is rotating at say 100 radian per second, what will be the velocity of the piston? What will be the velocity of the connecting rod? Right? So these all things needs to be determined. So in the second chapter, you are going to we'll use different techniques of velocity and acceleration analysis so that we are able to understand all these concepts. Right? And thereafter, we'll study gears in mechanisms. Now to build up the mechanisms, okay? Suppose you want to use the IC engine in a car, so you'll have to use power transmissions. For power transmissions, you'll require gears. So we'll see the basics of gears, right? Again, similarly for a vehicle to function, you need flywheels. Any machines to function, you need flywheels. So we'll see the what is a flywheel and what is its function and how does it perform, right? Again, balancing comes to be a very important part. Because without balancing, there's a lot of problems happen. So we'll see what is balancing and how the balancing works. So this whole subject is completely with respect to different machines. So we'll study different parts of a machine, right? And how all these things comes together and gives us a beautiful result, right? Even if you see an aeroplane, we just get to see the aeroplane, but we don't know what is going on inside. So in this chapter, we'll try to, whatever extent possible, we'll try to learn how the system works inside the aeroplane, kind of, right? So I hope you had a little bit of idea what exactly is a mechanism. Slowly, as we progress, as you will see different types of mechanisms, then you'll be able to relate it more easily, right? How a machine is converted, how a mechanism is actually converted into machine. So this is what is the summary of this chapter, right? So let us first start with the smallest part of a mechanism. Let us start with by knowing what is the smallest part of a mechanism. The smallest part of a mechanism is known as kinematic link or element. Smallest part of a mechanism. And how do we define this? We defined it as any part that is having some relative motion with respect to some other part is known as kinematic link or element. So definitely there must be some relative motion with respect to some other part, right? So if any part is having any relative motion with respect to some other part, it will be known as kinematic link or we'll get to see this. Okay. Now, just by reading the definition, you might not be able to understand. Now, even if I give you an example, that example will also be not very fruitful. You'll not be able to grasp this example. I'll come back to this line after few more slides, right? After a few slides, I'll come back to example. Then you'll get to know. Okay, I'll relate it to this, right? Some relative motion with respect to some other part. Right? So the smallest part of a mechanism is known as kinematic link or element, and it must have some relative motion. It must have some relative motion with respect to some other part. So we'll come to this point, right? So a link need not be rigid body, but it has to be resistant in the direction of transmission. For example, I'll tell you the example of a link: flexible link, fluid link, right? Deformation, rigid link. So what are rigid link? Rigid link are those links where the deformation is negligible, like connecting rod, the crank, the piston. These are all links. Right? And it has a relative motion with something else. For example, you take the piston. Piston has relative motion with all other parts. It has relative motion with respect to cylinder. It has relative motion with respect to the connecting rod. It has relative motion with respect to the crank. Right? Now, so the links where deformations are negligible will be known as rigid link. This is for your understanding. Right? Deformations are within the permissible limit. They will be known as flexible link. Right? Example, belt. So a link need not be rigid body. As you know, the belt is not a rigid body, but it is resistant in the direction of load transmission. So if you consider a belt, if you consider a belt drive, which drive? Belt drive. Konsa drive? Belt drive. So if you're considering a belt drive, right? So definitely it is flexible, but it is resistant in the direction of load transmission. Suppose it is this is the smaller pulley, it is rotating in this direction, so it is pulling this belt. So the belt will not extend in this direction. It will not elongate. Right? The length of the belt will not increase in this direction. Means it is resistant in the direction of load. Now, let me try to be more clear. Let me try to see if I can be more clear. Now, in place of this belt, if I connect this with a rubber band, do you think that this will also work as a link? Yes or no? Can you tell me? In place of the belt, if I take a rubber band, all of you have seen rubber bands, right? We use it daily to pack different things. Suppose we use a rubber band. We don't use a belt, but what we do, these are small pulleys. Let us assume these are all small pulleys. And we wrapped it using a rubber band. So do you think that rubber band will also act as a link? Yes or no?
Yes, sir.
All of you feel so? All of you feel so? Others are thinking? See, I'll tell you how to differentiate. I'll tell you, right? Now, if you see what I have told you, that a link need not be a rigid body, definitely, but it has to be resistant in the direction of load. Yes.
Sorry, sir. I was facing some issue with the mic, sir. I was trying to fix it when you were asking.
Okay. Now tell me, will
Yes,
the
sir.
rubber band will it be a link? Will you consider it to be a link?
So basically, the flexible links should have the tendency of transmitting the tensile forces only. So I don't think so, sir.
Why?
No, sir. Actually, it can act like because belt, rope, chains, wires, they all are flexible links because they're all used to. But sir, for what you say, for the connectable link, they share two properties. One is like to have the relative motion, second is a resistant body. So I think the rubber band cannot resist it.
Exactly. Very good. So the rubber band will not be able to resist the load. Do you really think the rubber band will be able to resist the load? No. It will elongate. It would
And so
elongate.
that's
What
a
happens
main
when you
reason that
apply force to the rubber band? What happens when you apply force to the rubber band? The rubber band expands its length, isn't it?
yes, sir.
Right. So that's why rubber band cannot be a link. Why not? Because it is not resistant. Resistant. Because it is not resistant in the direction of flow. Okay. So you have to be a little bit careful. So I hope this is clear to all of you, because it will extend on application of the force. It will extend. Okay. So you cannot consider
But
a
sir,
rubber
there
band.
will be like the biggest drawback of this one, like it can operate only the smaller RPMs.
Right. Exactly. Even a
Because
smaller
the
RPM also.
yeah,
You're talking about belt drives, or you're talking about rubber band?
no, it's a belt drive, sir.
Belt drives, exactly. No, it is not that smaller RPMs. Okay, it is not
But sir, on
necessarily
an average,
small.
when it compares with the gear trains, rigid links, and all, it will be comparatively small.
Yes, comparatively small, but you must be knowing in automobiles. So
Yes, sir.
the transmission shaft and your engine is actually connected using belt drives.
Correct, sir.
Right? If you open the bonnet of the car, you'll get to see that they are using belt drives to transmit the power.
Yes, sir. I've seen that. Yes, sir.
Right? So it is not
Right.
that belt drives will, you can design so, right? You can design V wells. We can design V wells so that they can
Yes, sir. They
actually
use V belt
transmit good
drive.
amount of RPM also. Okay? Good
Yes,
amount
sir.
of RPMs also. So there are still
Right.
problems. There are still problems with that. Okay? Definitely we'll prefer gear drive, and what are the limitations of belt drive and what are not, we'll see it later on. Okay? I'm taking it.
Right.
We'll see it later. Okay? So
Yes,
there
sir.
can also be fluid link, like power is transmitted using fluid pressure. Examples are your hydraulic jack, right? Pneumatic brakes, hydraulic brakes, right? So there are so many examples of pneumatic and hydraulic devices nowadays we use, right? So where we use Pascal's law, right? And we transfer the power from one part to the other, right? So you have studied Pascal's law now? Yes or no?
Yes, sir.
Yeah, fluid mechanics is over, right?
Sir, actually, it's going on, sir.
Going on. It's going. Okay, fine. So yes, so we got to know that the smallest part of a mechanism is known as link, right? Now we'll try to learn the different types of relative motions, We'll try to learn different types of relative motions, right? So basically there will be three types of relative motion possible: completely constrained motion, successfully constrained motion, and incomplete constrained motion. So what is completely constrained motion? Completely constrained motion is possible. Okay, where is a type of relative motion when motion is possible only in one direction, irrespective of the direction of force. Motion is possible only in one direction, irrespective of the direction of force. So if you take this example, a rectangular bar inside a block. So it does not matter in which direction you are applying the force. Even if you're applying the force like this, even if you're applying the force like this, even if you're trying to twist it, right? There is only one possible movement, that is in horizontal direction. Yes or no? You try to twist it, you apply force in whichever direction you want. If the rectangular bar inside the rectangle hole, if it moves, it will move only in the to and fro direction. It will have only to and fro motion in the horizontal direction. Yes or no? Are bolo, yes or no?
Yes, sir.
Are you able to feel it? So this kind of motion will be known as completely constrained motion. Motion is possible only in one direction, right? Then you have successfully constrained motion. Successfully constrained motion. So what is successfully constrained motion? Motion is possible in more than one direction. Motion is possible in more than one direction, but by using some technique, it is made to happen only in one direction. By some external means, it is made to happen only in one direction. Let us take an example. For example, if you have a cylinder inside a, let me say, a round cylinder inside, a round piston inside a round cylinder. So how many types of motions are possible for the cylinder? Can you tell me? How many types of motions are possible for this cylinder? How many types of relative motions possible between the cylinder and the piston? How many types of relative motion is possible between the cylinder and the piston? Yes, my question is how many types of relative motion is possible between the cylinder and the piston? Can I say there are two motions possible? One is the to and fro motion of the piston inside the cylinder, and one is rotation motion, rotation of the cylinder inside the piston inside the cylinder. Yes or no?
Yes, sir. Same as camshaft and all.
Right? There are only two types of motions possible. There are only two types of motions possible. Definitely more than one motion possible, right? Now, if I attach the connecting rod to the cylinder, if I attach the connecting rod to the cylinder, if I attach the connecting rod to the cylinder, now how many motions possible? Can I say the rotation of the piston? If I connect the connecting rod to the piston, can I say the rotation of the piston will be arrested?
So
Can I
only
say the
linear
rotation?
motion.
Yes, the rotation of the piston will get arrested. Now only the linear motion, the to and fro motion in the horizontal direction, that is only feasible. So what happened? Motion was possible in more than one direction, but by using some external means, we have restricted one of them and made to happen only in one direction. So this kind of motions are known as successfully constrained motion. This kind of motions are known as successfully constrained motion. The third kind of motion, third kind of relative motion, the third kind of relative motion is incomplete constrained motion. The third kind of relative motion is incomplete constrained motion. So what is incomplete constrained motion? Motion is possible in more than one direction. Motion is possible in more than one direction and is dependent on the direction of force or type of force. For example, a circular rod in a circular hole. Circular rod, you can see the diagram, circular rod inside a circular hole. A circular rod inside a circular hole. If we push the rod, it will move in this direction. If we apply some twisting moment, it will rotate. If we apply some twisting moment, it will rotate. So it depends, the type of motion completely depends on the type and direction of force. Right? So these are the three types of relative motions possible. Completely constrained, where motion is possible only in one direction, irrespective of the direction of force. Successfully constrained, where motion is possible in more than one direction, but by using some external means, we have restricted one of the motion and only one of the motion is allowed to happen. The third is incomplete constrained motion. Motion is possible in more than one direction, and the motion is dependent on the direction and type of force. So these are the three types of relative motions. Now use your common sense and tell me which type of motion would you prefer if you want to build a machine where you want a desired output. So machines, I'll give an example. For example, suppose I'm starting a car. I'm starting a car and I apply the first gear, right? Then slowly I release the clutch and then press the accelerator. In which direction do I want the car to move? I definitely want the car to move in the forward direction. Right? I definitely want the car to move in the forward direction because I have applied gear 1. Right? If I apply reverse gear, I want the car to move in the backward direction. So what do I want is that I want to be sure. Right? If I'm giving an input, I want to be sure of the output. Whatever the input might be, the car might be in a slope upward, the car might be in a downward slope, the car might be in a horizontal road, or whatever it is. If I apply the gear number 1, the car should move forward. If I apply reverse gear, the car should move backward. So whatever the conditions might be, right, I want a desired output. So desired output can be obtained only if the relative motions are either constrained or successfully constrained. Desired output is possible only if the relative motions are either completely constrained or successfully constrained. We'll never use any incomplete constrained motion in our mechanisms. We'll never use any incomplete constrained motion in our mechanisms because of the low surety what we are going to get as output. We don't have a definite output. So tell me, did you understand this concept? What is completely constrained motion? What is successfully constrained motion? And what is incomplete constrained motion? And what type of motions we will actually use in our mechanisms? What kind of relative motions we want to use in our mechanisms? Is it clear to everybody?
Yes, sir.
Just hold on. Okay. Now let us move on to a kinematic pair, right? So when we connect two kinematic links, we get a kinematic pair, right? So the connection between two links is always a joint or pair. The connection between two links, to connect two links, it will always be called as a joint or pair. But if it is called as a kinematic joint or kinematic pair, if the relative motion between the links is constrained in nature. So any two links, if you join them, it will be known as a joint or pair, definitely, right? It will be known as a joint or pair, right? But if you want to call it as a kinematic joint or kinematic pair, the type of relative motion between the links should be constrained, either completely constrained or successfully constrained, right? Either completely constrained or successfully constrained, right? So let us see some examples of kinematic pair. Let us see some examples of kinematic pair. For example, turning pair. Turning pair is also known as revolute pair or hinge joint or a pin joint. So there are two links here. Link number 1, link number 2. There are two links here, link number 1, link number 2. So if you want to understand what is a turning pair of a or a hinge joint, okay, you can imagine a scissor. You can imagine a scissor. Right? So the joint of the scissor is nothing else but a revolute pair or turning pair. All of you must have seen a scissor, right? All of you must have seen a pair of scissors, right? So the joint which joins the two hands of the scissor is nothing else but a revolute pair. It is also known as turning pair, a pin joint or a hinge joint, right? So this is the joint represented by. This is the joint. Okay, so if you have any doubt, you have to ask me. Okay, you can put it on the chat. Okay, if you have any doubt, you can put it on the chat. You can speak up the way you want. Then we have a sliding pair. Sliding pair is also known as prismatic pair. So if one, let me say this object slides over this plane surface, it is a sliding pair. You have to make sure that definitely if you just simply keep a block on surface, the motion won't be constrained. So you have to make sure that the motion gets constrained, means it is connected by a link or something like that. Right? Only then it will become a sliding pair or prismatic pair. Only then it will become a sliding pair or prismatic. You'll have rolling pair. Right? You have a rolling pair. You have a screw pair. You have a screw pair. Right? You have a spherical pair. So you can see in the rolling pair, right? The type of motion is different. Rolling motion. The type of motion is different. Rolling motion. Examples, you can take the examples of ball bearings. Right? Sliding pair, the type of motion is linear motion. Turning pair, the type of motion is rotation. So all the pairs have different types of motion. So what is the type of motion of a screw pair? I can say it is translation plus rotation. Rotation plus translation. Because the screw will rotate about its axis and also it will go down. Then you have a spherical pair. So what is the example of a spherical pair? There are a lot many examples of a spherical pair.
So, ball and socket joint.
Exactly, ball and socket joint. Right? Ball in socket joint is an example of a spherical pair. So generally you will get to see this ball and socket joint kind of pair in the rear view mirrors of the vehicles. Or bike, if you take a bike, see a bike, right? If you go and see the rear view mirrors of the bike, right? So you'll get to see a ball and socket joint. What are the other examples? Can you give me another example of ball and socket joint? I think which you use it regularly every day.
So pen stand.
Pen stand, yeah. Pen stand, yes. Lot many people do use pen stand. But there
Yes,
is
sir.
one joint, you have it on your body, right? That is your wrist.
Okay, okay,
Right?
yeah.
That is your wrist. What is your wrist? Wrist is an example of ball and
Ball and
socket
socket
joint.
joint.
Your soldier joint. Your
Yes.
soldier joint is a example of ball and socket joint. Right? Your ankle is, what do you think? What do you think is your ankle? What kind of joint is your ankle? Okay, let us not go to ankle. Let us say your arms and the soldiers are joined by we have three joints in our hands, right? So this is the hand. Let me say palm. I'm not very good at drawing, but I hope I will be able to explain it to you. This is your hand. So you have a wrist joint here. Then you have your arms. Then you have another joint here. Then you have your soldiers, you can say. Right? Then you have another joint here. Right? So these two are definitely a spherical pair. Can you tell me about this pair, this joint? What do you think about this joint? What do you think about this joint? What kind of pair do you think is this joint? Yes, it is a hinge, or you can say it is a turning pair. Very nice. It is a turning pair, right? It is a turning pair. You cannot rotate it. You cannot rotate your hands completely. You can only turn. You can only turn. But if you see your soldier, or if you see your wrist, you can move it in any direction you want. Right? You can move it in any direction you want. Right? You can move it up and down. You can move it sideways in any way. But you cannot move the joint between your arms and the shoulder in any direction. It is an example of a turning. Okay, so according to the type of contact, okay, that was whatever we have done, types of joints according to relative motion. What is the type of relative motion? Rotation, linear motion, right? Rolling motion, rotation plus translation. Again, spherical pair is a spherical motion, right? So according to the type of relative motion, these pairs are classified. Similarly, according to the type of contact, what kind of contact these pairs have? The kind of contact these pairs have, the lower pairs will have a surface contact. So any pair, any two links, if they have a surface contact, it will be known as lower pair. It will be known as lower pair. So most of the pairs will be lower pair. For example, turning pair will be lower pair, right? Because you'll have a surface contact here. You're going to have a surface contact here. Sliding pair or prismatic pair will be a lower pair. Will be a lower pair. Rolling pair. Can you tell me rolling pair? What kind of contact is this?
So point contact.
Yes, if it is a sphere, then it will be a point contact. If it is a cylinder, there will be line
Oh, that's
contact.
line contact.
This
Yeah.
will become
High
a
pair.
higher pair. Higher pair. Screw pair will again be a lower pair. Spherical pair will again be a lower pair, right? Because it has surface contacts. So this way you can classify lower pair and higher pair. And there is one more type of pair, right? Not frequently, not asked in GATE, but yes, in other exams, there might be questions on this. Wrapping pair, right? For example, belt drive, belt input. For example, belt input, wrapping pair. Okay, so this is according to the type of. Now let us see different types of joints. different types of joints. I'm talking about joints. I'm talking about joints, right? So what is a binary joint? If two links are meeting at a joint, then we call it as binary joint. Two links are meeting at a joint, we call it as binary joint. If there are three links meeting at a joint, we call it as ternary joint. If there are three links meeting at a joint, we call it as ternary joint. If there are three links meeting at a point, we call it as ternary joints. And if there are four links meeting at a joint, we call it as quaternary joint. If there are four links, any kind of, see, I've just shown you with one single line, right? These are rods. So the links can be of different types. Okay, any shape, size. For example, piston is a link. Cylinder is a link. It does not look like a straight line. For example, I'm giving you here, right? So that the diagram does not become very complicated. So if there are two joints meeting at a point, so it is known as binary joint. If there are three joints meeting at a point, it is known as ternary joint. If there are four joints meeting at a point, it is known as quaternary joint. Okay. Now, something very important. One ternary joint, this is binary joint B. This is binary joint B. One ternary joint is equal to two binary joints. How? Because if you see 1, 2 will form one joint, 2, 3 will form one joint. So using just two binary joints, you have used all the links 1, 2, 3. Similarly, how many binary joints can form four links? 1, 2. Let me say one binary joint. 2, 3, 3, 4. I have used up all the links. So similarly, you can say one quaternary joint is equal to three binary joints. So this is very important. This is very important, very, very important. Please remember, right? So one binary joint, this is one ternary joint is equal to two binary joint. One quaternary joint is equal to three binary joint. If n is the number of links connected to a joint, it is equivalent to n minus 1 binary joints. If n is the number of links connected to a joint, it is equivalent to n minus 1 binary joint. Okay. Apart from this, let me tell you about links also. ठीक है, यहीं पर बता देता हूँ, ठीक है, so that it becomes easy for you. ठीक है, types of links. Or let me share another thing. Types of links. Okay, क्या मैं let me share it to you. Types of links. One type of link is also like this. Binary link. So you have to remember the difference between link and joint. Binary link is a link where it is connected to 2 points. It is connected to 2 points. A link which is connected to 2 points. 2. Ternary link. Ternary link. A link which is connected to 3 points. Suppose this is a link which is connected to 3 points. There are 3 joints connected to this link. So this is known as ternary link. And then you have a quaternary link. Quaternary link. So here it is connected to 4 points. 2, 3. A link which is connected to 4 joints, right? This is known as quaternary. So you'll get more understanding of different types of links when you solve problem, right? When you solve problem, you'll get better understanding, much better understanding. Okay. So please remember type of joints and type of links. So these are all binary joint. Okay. You can see how it has been named: binary joint, ternary joint, quaternary joint. And what we have seen: binary link. This is a binary link. Then you have ternary link. Ternary link. Then you have quaternary link. Then you have quaternary link. Right? We'll solve problems. Problem here. Okay, no problem, no problem. We'll see. Anyways, we'll see this, right? So now let us move on to kinematic chain. Let us now move on to kinematic chain. After that, we'll enter into degree of freedom. I don't know if it will be possible in today's class. But let us see. Okay, let us see. Before that, I want to show you an example of links and joints. Okay, एक example देखते हैं, छोटा सा example. Let us see. Let us have an example. This kind of a mechanism. ये क्या है आपका mechanism? We'll solve this kind of mechanisms later on. We'll try to find out a degree of freedom of this mechanism. We'll also learn what is a degree of freedom. Now you can see how many links are there. Let us try to count how many links are there. So this is a kind of mechanism. Okay? Just for your understanding. Just for your understanding. Just for your understanding. Okay? Just for your understanding. Okay? Let me say this is a mechanism. How many links are there? Let us try to find out. This is link 1 link. This is 2 link. You can see this is a solid plate. This is a plate. If I have dash at 45 degrees, it becomes a solid plate. So this is link number 2. This link number 3, link number 4, link number 5, link number 6. Right? There are 6 links. Right? Okay. Now, if you see this point, I'll not go into very much detail, but let us see this point. Can you see that at this joint there are 3 members meeting? Yes or no? There are 3 members meeting at the joint, 4, 5, and 6. So what kind of joint is this? This is a ternary joint. Ternary joint. This is a ternary joint. Why? Because there are 3 members meeting at this joint. Right? If you look at this link, this is different here. This is a link. You have to understand the difference. This is the link. If you look at this link, how many connecting points does the link has? How many connecting points the link has? The link has 4 connecting points. You can see the link has 4 connecting points. So it is actually a quaternary link. Quaternary link. It is basically a quaternary link. There are 4 connecting points. So basically it is a quaternary link. It is a quaternary link. Right? So what kind of joint is this joint? This is a binary joint. You can see there are only 2 members meeting at this joint, link 2 and link 6. Link 2 and link 6. So this is a binary joint. What kind of joint is this? This is again a binary joint. 2 members are meeting. Link 1 and link 2 are meeting at it. Right? Link 1 and link 2 are meeting at it. So this is also a binary joint. What kind of joint is this? You can see there are 3 members meeting at this joint. 1, 3, and 4. So this is a ternary joint. Right? Similarly, this is also a binary joint. This is also a binary joint. So I hope you have understood what is the difference between a link, binary link, right? These are all binary links. This is a binary link. This is a binary link. Because it is connected only to at 2 places, right? This is a binary link connected at 2 places. This is a binary link connected at 2 places, right? So we'll see this kind of examples we are going to see, but I hope that you have understood what is the difference between binary link and binary joint, quaternary link and quaternary joint, ternary link and ternary joint. So is it clear? Tell me yes or no. Is it clear? Yes or
sir.
no? Great.
Yeah.
Great. So let us now see what is kinematic chain. What is kinematic chain? Let us see what is kinematic chain. Now, if all the links are connected in such a way that the first link is connected to the last link in order to have a closed chain, if all the links are connected in such a way that the first link is connected to the last link in order to have a closed chain, and if all the relative motion in this closed chain are constrained, then such a chain is known as kinematic chain. Then such a chain is known as kinematic chain. For example, let me see. Suppose this is a link. One more link is there. 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 So this way, the first link is connected to the last link. The first link is connected to the last link. And all the motions, all the relative motions in this closed chain are constrained. And we call it as a kinematic chain. We call it as a kinematic chain. We call it as a kinematic chain. If all the links are connected in such a way that the first link is connected to the last link in order to have a closed chain, and if all the relative motions in this closed chain are constrained, then such a chain is known as kinematic chain. Now the good part is not a kinematic chain. If we fix one of the links, the kinematic chain will become a mechanism. If we fix one of the links, fix one link. You fix any one link, the kinematic chain will become a mechanism. You fix any one link, the kinematic chain will become a mechanism. And you put this mechanism to use. Use it. Put to use. If you actually see, if you're able to use the mechanism in some productive way, it will actually become a machine. It will become a machine. So, see, we have come to know how exactly we will form a machine. First, the smallest part is the kinematic chain. Sorry, kinematic link. So, if two links are joined, you will get a joint. If the relative motion between the members are constrained or successfully constrained, that joint will be known as kinematic joint. If you can form a closed chain of such joints and all the relative motions are constrained, it will get a kinematic chain. And if in the kinematic chain, one of the link is fixed, we'll get a mechanism. And if the mechanism is put to use, we'll get a machine. So always remember, to use a kinematic chain, we have to fix one of the link. To use a kinematic chain, we have to fix one of the link. If you fix one of the link, it will become a mechanism. And if you use the mechanism, it will become a machine. Right? So this was the first part. Okay, now if we continue this, we will not be able to end it. Right? The next is the degree of freedom. Finding out degree of freedom. What exactly is degree of freedom? Again, that requires great detail of discussion. So we will end our class, today's demo class, at this point. I hope you're able to understand. Tell me if you have any doubt or any query, anything in your mind. Tell me if you have any doubt, anything in your mind. Yes, Pranit and Sahil.
Sir, it was clear, sir. It was pretty much clear.
What about Pranit? Is it clear? Was it clear to you? Okay, great, no doubts. So this is how we will cover up. It will take approximately 25 to 30 hours. So it means somewhere around 12 to 15 classes, right? So the first 2 classes will be mechanisms. It might go even beyond 2 classes. We'll try to finish up mechanism in first 2 classes. The next 2 classes will be velocity and acceleration analysis, to 4 classes. Next 2 classes will be gears and gear trains, 6 classes. The 7th class will be flywheel, or sorry, the kinematic analysis of slider crank mechanism. 8th class will be flywheel. 9th class will be governors. 10th class will be gyroscope, balancing, gyroscope and cams and followers, we can say. Okay. 11th class will be balancing, right? And if required, we'll have in between we'll have some doubt sessions. Okay, that doubt sessions will also be there. So approximately you can consider you will have somewhere around 25 to 30 hours. Okay, thank you. If you have any doubt, you can ask.
Thank you.
Thank you. Thank you so much. Thank you so much. So I'll end the meeting. I'll stop the recording. Hope to see you in missing class. Shall I end the meeting? Okay, great. Pranit? Thank you, Sai. Thank you so much. Okay, good night, have a nice sleep. Best wishes, prepare hard, right? Don't stop, prepare hard.